December 1984, the scene of the worst accident in the history of the chemical industry. Over 2,500 people died, and many tens of thousands were injured when a runaway reaction occurred after water entered a storage tank containing methyl isocyanate. Seveso, Italy, July 1976. A few kilograms of highly toxic dioxin were released from a reactor venting to atmosphere after a runaway reaction. People were injured, though nobody was killed, and there was widespread environmental contamination which caused large numbers of people to be evacuated and to be kept away from their homes while a major cleanup operation was carried out. The consequences for health and safety legislation were far-reaching. Concern over this and other incidents was the main impetus for the EEC directive on the major accident hazards of certain industrial activities, the so-called Seveso Directive. This and subsequent amendments have been implemented in the UK by the Control of Industrial Major Accident Hazards Regulations 1984 and later amending regulations. Runaway reactions are not new. This incident in Yorkshire in 1930 involved a runaway exothermic nitration. 12 people were killed in the explosion, about 50 were injured, and 500 were made homeless. Damage to plant can be caused directly by a runaway reaction and may be made worse by fires and explosions of flammable materials released from vessels damaged by overpressure from the exotherm. Not all incidents are this dramatic, but runaways continue to happen. They can cause major damage and usually have potential for serious injury unless precautions to mitigate the effects are carefully planned. Even an incident which causes no damage or injury involves financial loss, so there should always be incentives to prevent runaways. The rest of this video will explain how this may be achieved, by first summarizing what runaway exotherms are and how they happen. It will then describe the importance of proper planning of reactions, how they should be prevented from running out of control, and what measures should be taken if they do. The final part will summarize sources of further advice. A chemical reaction invariably involves an energy change. In other words, heat is either absorbed or released. If heat is absorbed, the reaction is said to be endothermic. If heat is given out, and the most obvious example is the burning of a fuel in air, the reaction is said to be exothermic. Some reactions occur as soon as the reactants come into contact, but in many cases heat must be applied to get a reaction started. Anyone who has struggled to light a domestic coal fire will appreciate this. Once it gets going, it continues with further evolution of heat. This is the case in many industrial processes, and we'll see later the importance of temperature control. In practice, exothermic reactions are far more common than endothermic reactions. All exothermic reactions proceed faster at higher temperatures. The temperature of the reactants will continue to increase if the rate of heat generation exceeds the rate of heat removal. Eventually, the temperature will rise exponentially and the reaction will run away. The pressure will also rise very rapidly in a closed system, or if the outlet from a vessel is restricted. This can have disastrous consequences. Many different chemical processes have been involved in runaway incidents, but this table shows the most common of these. It is not exhaustive. This video will concentrate on runaway reactions in batch process reactors, but runaways can happen in other circumstances. For example, exothermic reactions may occur during bulk storage. Materials mixed in this bulk waste tank started to heat up due to an unexpected exothermic reaction. The tank was cooled sufficiently to stop a runaway, but the cooling water caused the inadequately designed bun to collapse. Drum storage may also be involved if, for example, unreacted materials are still present when product is drummed off, or perhaps if dirty drums are used. In this incident, pre-mixed materials for a reaction were stored temporarily in 2 drums, but these were inadvertently heated when they were placed near a hot still. A runaway reaction occurred. One drum emptied through the bunghole, while the other blew apart. Some materials, such as acrylic acid, can undergo self-polymerization, and here drums are gently shaken to keep an inhibitor well mixed in. Runaway exothermic polymerization can occur with stored ethylene oxide. The reaction is catalyzed by a wide range of impurities which must be kept out of storage tanks. Road tankers have been involved in incidents. In one case, the contents of a tanker were almost boiling when it reached its destination, and only emergency cooling by the fire brigade prevented a major incident. The reaction was caused by the load mixing with residues from a previous load. This is the damage caused by a runaway polymerization of glacial acrylic acid in a road tanker. A man was killed when wrong materials were inadvertently mixed, causing a violent reaction which blew this way vessel apart. Disposal of waste laboratory solvents can be hazardous. 2 people were injured by flying glass when a violent reaction occurred as chloroform was added to a residue bottle for contaminated solvents from chromatography, and which included acetone. The reaction was believed to have been catalyzed by impurities present. Exothermic reactions with potential for runaway can also be present on continuous process plants. In other cases, the hazard arises from an exothermic decomposition, particularly from overheating. This test shows what happens when about a ton of a product was deliberately heated to its decomposition temperature. If a distillation is continued until all solvent is removed, remaining products may decompose exothermically, and this is what happened here. Even without distillation to dryness, residues of raw materials or products can undergo runaway decomposition during solvent recovery if the still operating temperature is too high or cooling is inadequate. Any method of heating chemicals, such as a dryer or drum melting cabinet, may cause decomposition problems for sensitive materials, particularly if heating controls fail and overheating occurs. Disastrous overpressurization can perhaps most readily occur if one of the products of a reaction is a gas or vapor, and the reaction proceeds more quickly than the venting arrangements can cope with. This is why the manway cover was blown off this reactor. Material was added while the stirrer was stationary. When it was started up, the reaction which followed generated large volumes of a gas very quickly. Having examined the circumstances in which runaway reactions may happen, the next question is, what goes wrong? This study in 1983 examined the prime causes of 169 incidents. The majority of these, and indeed many incidents since, were caused by certain classic problems, which are summarized in this table. More often than not, combinations of factors were involved, and simple failures of safety backup systems contributed to the severity of incidents. A look at a selection of incident photographs will provide some dramatic illustrations of many of these points. Decomposition of the contents of a still caused this damage after the man lid blew off. Flammable vapors were released and exploded. The still had been shut down to attend to a minor leak, but the steam heating was left on. The still contents were contaminated by accumulated residues from poor cleaning between batches. The contamination probably catalyzed the decomposition. The vessel was not vented. In this incident, unstable compounds formed during the 6 months material was in storage before distillation was attempted. And here, hydrochloric acid, which was formed in the process, reacted with the mild steel reactor. The ferrous chloride produced had an autocatalytic effect and accelerated decomposition of products to the point of runaway. Laboratory hazard testing had been done using stainless steel rather than mild steel. This incident occurred when a new, more efficient catalyst was used for the first time. Also, the temperature control was misaligned, allowing overheating by 10 degrees Celsius. A partial failure of the jacket cooling system was another factor. Failure to take proper account of heat transfer requirements when scaling up processes has led to a number of incidents. Here, the reactor was wrecked when the process was moved from a 500 to a 1,300-gallon reactor. Contributory factors were the addition of the final portion of catalyst at a higher than normal temperature and the thermometer pocket being too short to give accurate temperature measurement. The final straw was the blanking off of the vent line because bursting discs had been failing under vacuum. Again, scale-up problems caused a vessel lid and stirrer to be blown 50 feet through the roof, and a gearbox landed 250 feet away. A steam-heated vacuum dryer overheated product, causing an exothermic decomposition. The heating control was a simple throttle valve and was ineffective. Additionally, no temperature monitoring instruments were provided on the vessel, and the vessel was not vented. A heating oil temperature control failed on this resin reactor, and the resulting overpressure caused the flange joint to fail. The reactor was vented, but the bursting disc had been fitted upside down and did not operate. A manually controlled process at this factory was left in the charge of a trainee operator during the heating cycle. He went elsewhere, and while he was away, the reactor temperature rose from 180 degrees to 368 degrees Celsius before the manhole cover blew through the factory roof. Charging errors can arise in a number of ways. Here, reactant quantities of 17.5 gallons and 155 gallons were transposed in error, possibly due to a poor process instruction sheet. Similarly here, a chemist transposed two figures when copying out batch instructions for a process operator. And in this case, the reactor top was blown off and the stirrer ejected because gross misproportioning of reactants took place. Water was not drained from an aniline stock tank, and the material fed to the reactor consisted largely of water instead of aniline. The problem at this site was that part of a batch was left in the reactor when a new charge was added. The reactor overpressurized because it was hydraulically full when the new batch started to react and liberate a gaseous byproduct. Human error during maintenance can cause problems. Steam was applied to clear a blockage in a transfer line at this plant. This raised the temperature of product remaining in the reactor to its decomposition point. And here, cooling water valves were not reopened after a maintenance shutdown, so proper cooling of the reaction was never established. When the violent exothermic reaction occurred, the plant damage was very considerable. The reactor vessel was fitted with a relief valve, but for fire or nitrogen overpressure only. Vents were either not fitted or were grossly inadequate in these incidents. And here, a reactor vented to this catchpot, and it in turn was vented to atmosphere. But the ultimate vent was too small, and the catchpot ruptured when a runaway reaction discharged into it. The runaway itself was caused by inadequate cooling, when a valve on a reflux return line was closed in error. Poor training may well have been a contributory factor in many of the incidents described, but was specifically commented on in the investigation of this incident. The operator in charge did not know what to do when he saw the temperature rising rapidly, and a more experienced operator also present had not recognized that the reaction was proceeding much faster than normal. Similarly here, the operator was not clear what he should do when the reactor temperature rise was noted. Runaway reactions causing injury and damage continue to occur, often due to one or other of the classic causes illustrated by the incidents described. A strategy for preventing such incidents is required. Understanding the properties of materials and the chemistry of both materials and reactions is essential for process safety. Where possible, a process should be planned as a semi-batch reaction rather than an en masse batch reaction. This reduces the amount of unreacted chemicals present should control be lost, limits the potential hazard, and can simplify and reduce the cost of safety measures. As well as the intended reactions, unintended side reactions, including possible decompositions of raw materials, intermediates, and products, must be considered. A systematic approach could well involve data collection, then a preliminary desk screening for obvious hazards, for example by identifying reactive groups or analogous substances or reactions, followed by laboratory thermal hazard testing, and often including pilot plant work before commercial-scale production can begin. Some of this work may need to be repeated if any changes are made to established processes. The booklet entitled Guidelines for Chemical Reaction Hazard Evaluation, produced by the Association of the British Pharmaceutical Industry, contains valuable advice and includes a useful assessment strategy summarized here as a flow diagram. Literature searches should form part of the initial data collection and desk screening stages. Two particularly useful sources are Bretherick's Handbook of Reactive Chemical Hazards and the National Fire Protection Association's Manual of Hazardous Chemical Reactions. These two volumes contain useful information on hazardous features of chemical reactions, which is not as readily available as that on individual chemicals in standard reference books. A range of chemical, thermodynamic, kinetic, and other data will be required to design a process and develop a reaction control strategy. Unfortunately, this data cannot be obtained from one simple test. Some major companies have their own facilities for carrying out the testing required, and services are also available commercially. The main types of test available include basic screening tests, isothermal calorimetry aimed at quantifying reaction kinetics and heats of reaction for particular reaction systems, adiabatic calorimetry used mainly for examining the runaway potential of reactions and individual compounds, and reactive venting instruments, intended primarily to provide data to enable calculation of vent sizes, but which also give some thermal data. A runaway reaction in even a laboratory-sized sample can have considerable destructive potential. Fortunately, this test was being conducted inside a substantial vessel which safely contained the reaction overpressure. Because of the potential hazard, certain tests may need to be carried out behind protective screens, in fume cupboards with strengthened windows, in armored fume cupboards, or even in specially designed blast cells. For the sake of clarity during filming, most of the test equipment shown is set up without protective screens. Relatively simple tests using inexpensive equipment can be used to obtain much of the data required for reaction safety. Simple insulated vessels called Dewar flasks are used for many of the tests, as these simulate the heat loss from full-scale reactors. This reaction calorimeter is an example of equipment which uses a Dewar flask. Variations of this have been made by a number of industrial companies. Reaction mixtures can be dosed into the Dewar vessel fixed into a water bath. By allowing a reaction to occur in the Dewar, the initiation temperature of any exotherm can be determined. This particular reaction calorimeter can only investigate reactions taking place at atmospheric pressure. But this adiabatic Dewar calorimeter is a more sophisticated piece of equipment, which uses a stainless steel Dewar vessel designed to operate under pressure. This instrument is used particularly for investigating runaways resulting from mischarging reactants, loss of agitation, or loss of cooling. It also has a dump tank, so by relieving the reacting mass, some information on venting requirements can also be obtained. The thermal decomposition of single substances can be investigated using this equipment. The test sample is loaded into a stainless steel tube and can be left to decompose at ambient temperature or heated until a reaction occurs by using the oven. The temperature at which the exothermic decomposition occurs is recorded. The onset temperature of decomposition is usually higher in small-scale tests than that which occurs in plant conditions, so great care is needed in scale-up of test results. This incident involved a violent exothermic decomposition at a temperature between 120 and 130 degrees Celsius, although laboratory tests had indicated problems only at 274 degrees and above. More sophisticated equipment is available commercially for carrying out tests similar to some of those just described. For example, this reaction calorimeter is used to determine heat flow of chemical reactions. This data is used to determine the cooling capacity requirements of full-scale processes. The reaction proceeds in a double-walled stirred tank reactor fitted with a stirrer and facilities for controlled dosing of reactants. Very rapid flow of a silicone oil heat transfer fluid through the reactor jacket keeps the reaction mass at the desired temperature as the reaction proceeds. The heat generated is removed by the heat transfer fluid and can be measured to allow determination of the amount of heat produced. The computer records the exotherm. This apparatus is used for studying controlled reactions. The accelerating rate calorimeter can be used to determine the temperature at which a substance will start to decompose, the time to maximum rate of reaction, and the point of no return. That is the critical temperature at which it would be impossible to re-establish control once a runaway has started. The substance under investigation is loaded into a small sample bomb, which is placed into the calorimeter chamber. The complete calorimeter unit is housed inside a substantial blast shield. The sample is heated in stages until exothermic decomposition occurs and no further reactions take place. Laboratory tests must be done properly. The material which decomposed, causing this damage, had been tested, but using an incorrectly sized sample tube for the instrument in question, causing a false result. The test did not, therefore, indicate the exotherm which occurred. When developing a process, laboratory studies will often be followed by pilot plant production. Hazard and operability studies can be used for a systematic examination of what could go wrong with a reaction. The application of the traditional HAZOP guide words to batch reactions is well established and can deal with variations in both materials and process conditions which may lead to problems. The information obtained from all the investigations should be recorded and will ideally be in two forms: a detailed technical process dossier and clear, simple operating instructions for both normal and abnormal conditions. The detailed technical process dossier is for use by technically qualified personnel and may contain this sort of detailed information. The instructions for use by plant operators need to show clearly and precisely each stage of the process and the measures necessary for it to proceed safely. They will typically be written in a step-by-step format. The operator will normally be required to keep records of each process stage and signed to indicate its completion. This may be done on detailed operating instruction sheets. The same provision could be made on a batch sheet which summarizes the operating instructions. The first instruction for any batch process should be to ensure that before charging starts, the plant is empty, clean, and where necessary, dry, that it has been properly assembled, and that all valve settings are correct. Other details will vary from process to process, but typically the quantities, order, and rate of charging for reactants and catalyst will be shown. The need to switch on the stirrer will be specified, and heating and cooling instructions will be given. Expected process temperatures and perhaps pressures will be given with maximum permissible deviations and emergency action. Details of other precautions, such as the use of personal protective equipment, should be included. The aim of all the investigations just described is to provide sufficient information on which to base a control strategy which should ensure that a reaction does not run away. The essential elements of this control strategy are correct charging of materials, reactor cooling, agitation, temperature control, pressure control, and instruction and training. It mustn't be assumed that any one control measure by itself is totally reliable and will always work. Some reference will be made later to duplication and backup facilities. Let's look at the first element in the control strategy, the correct charging of materials. The specific problems associated with charging include charging the wrong material and charging the correct materials but in the wrong amounts, the wrong order, at the wrong temperature, or at the wrong rate. It will be obvious that trouble is likely if the wrong materials are added to a reactor, so the correct labeling of materials and feed lines is essential. The control system at this transfer point has been carefully designed to prevent hoses being connected to the wrong feed pipe for the reactor in use. The significance of adding materials in the correct order, in the right quantities, at the right rate, and not missing any out, is less obvious, but is equally important. Here, for example, a weigh vessel is mounted on load cells so that correct quantities of reactants can be accurately charged. And here, a radioactive level gauge fitted to the reactor would detect any attempt to double charge the reactor. Arranging the reactor charge so that a number of whole bags of material are required, rather than part bags, and then only delivering the right number of bags to the reactor, is another way of trying to avoid charging errors. This flask contains catalyst being metered gradually into a reactor. Whether catalyst is charged this way or in one lot, under or overcharging catalyst may be just as important as correct charging of reactants. Adding materials or catalyst at the correct temperature may also be critical. Too low a temperature and the reaction may not start, causing an accumulation of unreacted material. This may react very rapidly and suddenly once it does begin. Too high a temperature and a violent reaction may occur straight away. Contamination of materials has often been implicated in incidents. Water has frequently been the culprit. Here, for example, water siphoned back into a reactor from a quench tank and reacted with oleum present to raise the reactor temperature to the decomposition temperature of the product. Contaminants on other occasions have themselves undergone thermal decomposition or catalyzed unexpected reactions. The use of clear and precise process instruction sheets can be of great assistance in ensuring that charging takes place correctly. cooling is an essential control for all exothermic reactions. The relationship between the rate of heat generation and the rate of heat removal is often misunderstood. The rate of generation of heat by reaction often increases exponentially with temperature. The rate of heat removal increases approximately linearly with temperature. As long as the rate of heat generation remains below the capacity of the plant to remove it, the reaction is under control. At a critical temperature, the rate of heat generation becomes equal to the rate of heat removal. If the temperature rises beyond this point, the reaction will run away because more heat is being generated than can be removed. This is why cooling failure, agitation failure, and temperature alarms are so important. Errors in calculating cooling capacity during scale-up from laboratory to pilot plant, or from pilot plant to commercial scale, can result in a reactor with inadequate cooling. A variety of cooling techniques may be employed, either singly or in combination. Internal cooling coils are commonly used. A reflux condenser may provide the main method of cooling, or at least contribute to the total cooling capacity. And of course, natural convection and conduction through the reactor surfaces will also assist. Coolant may be circulated through an external jacket on the reactor. In addition, coolant in cooling coils or a jacket may be circulated through an external heat exchanger. The cooling medium will most commonly be water, with sometimes brine or glycol used to give greater cooling capacity. Whatever the methods chosen, the cooling system must be sufficient to control all expected exotherms and have spare capacity to deal with unexpected temperature rises. The controlled addition of reactants may provide the primary means of temperature control in some reactions. But even in these cases, provision of cooling will be required as a backup for emergency control purposes. In the case of en masse reactions, where a complete charge of materials is added to the reactor in one go, cooling may provide the primary means of control. Case histories show that human error is an important cause of cooling failure. For example, the operator simply forgets to turn on the coolant or sets the flow rate incorrectly. Loss of cooling can also be caused by pipe blockages or pump failures. Coolant failure alarms should normally be provided. A flow meter on the coolant supply, ideally on the outflow from the reactor, is one method of providing a signal to a coolant failure alarm. Other ways are to measure the pressure in the coolant pipework and link this to an alarm, or monitor the difference in temperature between coolant feed and outflow. A visible indication of coolant flow, again ideally at the outflow, is desirable. Temperature control is so crucial that coolant must come from a reliable source and a backup supply may be necessary. A site may, for example, take town's water in to provide its primary coolant supply, but have a borehole supply on site to provide backup. Either may feed a recirculation cooling water system using cooling towers, or be fed directly to reactors if necessary. A stored water supply of sufficient capacity to allow safe shutdown of a reactor if the primary coolant supply fails may also be provided. Proper mixing of reactor contents is essential, both to prevent accumulation of unreacted material and to ensure adequate heat transfer and hence cooling. A suitable stirrer will nearly always be required to achieve this. Operator error again shows up in case histories as a major factor in incidents. The operator may forget to start the stirrer until reactants have accumulated. Then, realizing his error, he starts it, producing rapid mixing, rapid reaction, and a runaway. Sometimes the operator may deliberately stop the stirrer for what at the time seems like a good reason, to collect samples, fear of overfilling, or on noticing process deviations, for example. Equipment failures may also cause loss of agitation. Motor or drive failures may occur. Stirrer blades may shear off, particularly if a reaction mixture is viscous, or securing bolts may corrode if materials are not adequately specified. A stirrer failure alarm should be provided. Simple indications that the stirrer is running should not normally be relied on because of the possibilities of stirrer blade and shaft failures. Monitoring current draw on the stirrer motor with an ammeter can be useful if the normal rate is relatively constant. A sharp decrease could indicate stirrer blades had become detached. An instrument which gives a positive indication of agitation, such as a shaft rotation sensor, for example, should normally provide the signal to the stirrer failure alarm. This plant has a device to detect motion of the surface of the reactor contents to indicate the agitator is still working. Stirrers can come in a variety of designs, and it's important to choose the right one. As this incident shows. An anchor-type stirrer had been fitted to the reactor, but it was changed to this less efficient propeller type shortly before the incident. It was unable to mix effectively a denser than usual batch of components. One of them accumulated around the edge of the reactor. This mass of separated material eventually reacted suddenly, leading to a runaway and a major explosion. Obviously, proper control of temperature is vital. Where possible, the heating medium chosen should be incapable of raising the reactor or plant to the temperature at which a runaway reaction or decomposition can occur. For example, low-pressure steam limits the reactor temperature here to about 135 degrees Celsius. Hot water would limit the maximum possible temperature even further. A reactor should be fitted with a high-temperature indicator and alarm system. Where the feed rate of reactants controls the reaction, automatic shut-off valves can be actuated by a trip system to cut off feed if the reactor contents exceed a certain temperature. A low-temperature alarm should also be fitted if there is a danger of materials accumulating without reacting. Again, case histories show that operator error features in many incidents. For example, failure to set or read an instrument correctly, or failure to adhere to process instructions. Equipment problems can also occur. For example, a single temperature instrument may fail. A duplicate may be needed. On a chart recorder, a pen can stick. Temperature probes must be in the reaction mixture and not be in the vapor space above the liquid level. Particular attention is needed at this point if batch sizes are reduced or if temperature probes are replaced. Certain agitator designs are prone to create a vortex in the reactor contents, and in a small batch may also leave the temperature probe exposed and giving an incorrect reading. In a number of cases, reactors must be heated to get a reaction started and then cooled in later stages of the reaction. The heating medium must be accurately and positively controlled. The supply of additional unwanted heat from a valve left open, or a passing steam valve, for example, could dangerously accelerate the rate of reaction. Temperature measurement alone may not give a sufficiently rapid indication of a potential runaway. In some cases, pressure monitoring may be required, particularly where one of the reaction products is a gas. A high-pressure alarm and perhaps a trip should be fitted where necessary. Instruction and training play a vital part in the safe operation of all chemical processes. Operators should be aware of the significance of every stage of a process and the safe procedure to be followed. They should be able to recognize abnormal conditions which may occur and know the procedures to be followed in given circumstances. Additional training should be given if any changes are made to process conditions, materials, or plant. Process instruction sheets may serve to remind operators of the detail of the stages of a reaction and must be followed. But operators must also understand the reasons for each step and not follow them blindly. Instruction and training are one element of the control strategy. However good they are, they must not become substitutes for the other elements. The strategy just described should keep a reaction under control. But if it starts to run away, it may still be possible to regain control and prevent a disaster. Disastrous runaway reactions rarely happen with no warning. The process may deviate over a substantial period. Training of operators in recognizing potentially dangerous deviations is essential. A variety of measures may be incorporated into a plant design to enable control to be re-established, to stop the reaction, or to allow it to run away safely. Alarm and trip systems may be arranged to cut off reactant feed if a process starts to run away. This may in itself re-establish control. Additional cooling may be possible, for example by switching on secondary cooling coils, or using cooling coils as well as reactor jacket cooling or limpet coils, or by switching to brine or chilled water instead of normal mains water, or by switching on a second chiller unit operating at a lower temperature than the normal chiller, or bringing in additional pumps to increase the coolant flow rate. The reaction mass itself can also be recirculated through an external heat exchanger. In the case of storage, firefighting water may provide secondary cooling, as on this ethylene oxide storage tank. Normally it would be cooled by a refrigeration system. Dumping the reactor contents rapidly may be possible. The dump valve opens and reactor contents are diverted from the normal process route to a drowning tank instead. This one contains water, but the drowning medium must be carefully chosen. The large dump valve at the base of this reactor opens automatically if instruments sense an unacceptable temperature rise. It can also be actuated manually. But either way, reactor contents are rapidly discharged to an external dump tank. It's fitted with a foam suppression system for control of fume and to fight fire if necessary. An alternative may be to quench the reaction and crash cool by dumping a large quantity of water or other suitable solvent directly into the reactor. The choice of quenching medium is critical. Here, for example, water is acceptable, but it has to be demineralized water, as even trace impurities could cause other adverse reactions. Just as catalyst addition may be required to initiate a reaction, removal of a catalyst may stop a reaction which is starting to run away. Where catalyst is added gradually, trips can stop the catalyst feed. But where the catalyst has been added in bulk at the start of a reaction, removal will be more difficult and may be impossible. On this plant, 2 out of 3 probes detecting excess temperature actuate a short stop system. This causes a chemical, which neutralizes the catalyst, to be injected very rapidly from this vessel into the reactor. Such arrangements are not very common. As we've seen, reactor safety may be based on process control, crash cooling, dumping, quenching, reaction inhibition, or various combinations of these. The most appropriate methods for each plant and process should be selected. Venting arrangements provide a final additional safeguard on most plants if a reaction still cannot be controlled. Venting is a complex topic which needs to be examined in some detail. There are some circumstances in which it may not be necessary, possible, or desirable, and these need to be considered as well. Venting arrangements vary, but the ideal vent is as large, short, and straight as is possible. Complex vent systems with numerous bends may be suspect, as the back pressure created by such a system may prevent reactor pressure from venting quickly enough. More complex vents are often unavoidable and are acceptable, provided their adequacy has been carefully calculated. Reactors may relieve into vent ducting through either relief valves or bursting discs. Relief valves have the advantage that they should reseat once excess pressure has been reduced, so avoiding the loss of large quantities of material. But they suffer from the disadvantages that the relief area is limited and the valve may block. Bursting discs are made to a variety of designs and specifications. They come in a range of sizes. They're less prone to blockage problems, but once they rupture, they cannot reclose. They're commonly used in pairs, with the space between monitored for pressure to detect premature failure of a disc. Combinations of relief valves and bursting discs may be used. Here, a slight overpressure would relieve via the relief valve, which can reseat, but a major pressure rise would vent via the bursting disc. At this installation, 3 vents are provided. The first deals with overpressure with a motorized valve and vent pipe, discharging to a catchpot. The second goes to the same catchpot vent line via a relief valve protected by bursting discs if the overpressure is greater. The ultimate relief is direct to atmosphere at roof level via bursting discs. Bursting discs and relief valves may be used in series, with the disc preventing blockage of the relief valve by chemicals during normal reactor operation. This building, with one wall of plastic sheeting, consists of a series of blast-proof cells housing open-topped reactors. Any runaway would vent into the cell, and ultimately to atmosphere via the lightweight wall. Personnel obviously have to be totally excluded from the cells during operation. Relief discharges must be disposed of safely. The physical form of the discharge will influence the options available, but these will include separation, direct discharge to atmosphere, treatment by a variety of techniques including flaring, scrubbing and neutralizing, and containment for later treatment. Where it is acceptable to vent directly to atmosphere, vents still need to be in a safe place. Vents should not discharge to areas where personnel may be passing or working. A knockout pot, such as this one, will trap liquid carried out of a vent system, but will allow vapors to discharge to atmosphere at a safe height. Catch pots are designed to contain all the vented products, so will themselves be pressure vessels, and correct design is important. A catch pot will normally be protected against serious overpressure by its own vent, which may be open, or fitted with a bursting disc. This has to go to atmosphere, but would be designed to provide last resort protection to prevent the catch pot rupturing, and not only releasing hazardous material, but generating missiles as well. A catchpot for highly toxic materials would be designed as a high-integrity pressure vessel to give total containment in all foreseeable circumstances. This catchpot was not adequately vented, nor strong enough, and ruptured when a runaway reaction vented into it. The forces applied to plant during a relief discharge can be very substantial. It's essential that pipework and vessels are designed with this in mind and are properly anchored and braced. A scrubber may be used to take the discharge venting from a reactor in some circumstances, or scrubbers may be fitted to the final vents from catchpots to remove any residual toxic materials if necessary. The efficiency of relief devices may be adversely affected by downstream discharge treatment or containment facilities, and these need to be carefully designed to avoid this. Authorities responsible for enforcement of environmental pollution controls may well have an interest in reactor venting and relief discharge disposal, and may need to be consulted. The size of a reactor vent is important, and the reason for choosing a particular sized vent should be on record. Where this is not the case, users may be asked to justify the relief design in use. The Health and Safety Executive has published a research report which compares the various methods available for the sizing of vent lines. A major multinational research project was undertaken under the auspices of the American Institute of Chemical Engineers between 1976 and 1986 to develop new methods for the design of relief systems. The investigation of two-phase flow, that is, the discharge of gas and liquid together through a vent when a relief device opens, was of particular interest. This is what happens, or would happen, with most reactions of practical interest. The phenomenon is not unlike the effects witnessed when a champagne bottle is opened rapidly. A frothy mixture will leave the container, which in some cases can be completely emptied. Two-phase flow through a relief designed for vapor or gaseous flow means less gas can leave because part of the flow is choked with non-compressible liquid. In extreme cases, this could cause overpressurization of a reactor and an explosion. Hazard Evaluation Laboratories' Phytech adiabatic calorimeter, Faust & Associates reactive systems screening tool, and the Fike vent size package are three instruments which have been devised embodying the Dyer's technology to enable vents to be sized directly to accommodate two-phase flow. Emergency venting is not always provided on reactors. Emergency venting may not be necessary if a reactor can withstand the maximum pressure rise in the event of a runaway. It may not be practicable for certain very energetic reactions, and may not be desirable if highly toxic products are involved and catchpots are not possible. In such circumstances, high-integrity control measures and perhaps sophisticated shutdown systems will be required. These will usually involve computers, and the level of safety achieved will need to be demonstrated, normally by quantitative risk assessment techniques. The safe operation of exothermic processes can be a complex topic, but certain basic precautions can prevent the vast majority of runaway reactions, or at least ensure that the runaway is safely contained. This video has summarized these precautions and demonstrated with photographs of incidents what can go wrong. More information may be needed. There is a great deal of published data in the scientific literature, which libraries will be able to assist with, but a few particularly useful references are included here. The Institution of Chemical Engineers has published a Guide to Chemical Reaction Hazards and Guidance on Relief Systems. The safe production of phenolic resins is dealt with in a publication from the British Plastics Federation. Publications and computer software relating to the dyer's work on reaction venting can be obtained from the American Institute of Chemical Engineers. Finally, the Institution of Chemical Engineers publish a list of consultants, a number of whom are active in this field, and who'll be able to assist with more complex problems. They should be aware of current developments in what is, and will remain for some time to come, a subject of substantial continuing research.